So, hello again, everyone. The keynote is titled From Research to Production, Enabling Real-World Applications with Conversational AI. The keynote would be held by Zenodia. She's a data scientist with many years of experience. She has also experience in training large language models, such as Megatron, LM from NVIDIA. And she works for NVIDIA as a deep learning solutions architect. And the other keynote is Adam. He's an applied research scientist with a wide range of applications in very different domains. For example, he worked in introducing machine learning capability to UK government. He worked also in self-driving cars and embedded and big data applications. And he also works as a deep learning solutions architect at NVIDIA. So thank you for being here, Zenodia and Adam, and I'm very excited about the keynote.
Here we go, outstanding. Thank you kindly for hosting us today. Let us crack on. Can I hijack the screen?
Yeah, I think it's okay, Adam.
Sure.
Take it away.
Waiting for the blessing. Share the screen. It's contemplating a share screen. Here we go. Screen number 2, share sound, and we're ready to go. Optimize for video clip because we do have waiting for the blessing. Share the screen. It's contemplating a share screen. Here we go. Screen number 2, share sound, and we're ready to go. Optimize for video clip because we do have one share. And now full screen. So here we go. Once again, good morning, and thank you for hosting us here today. So what we're going to talk about is our approach. So NVIDIA's approach for translating the research that we do internally on broadly understood conversational AI, and large component of that is also natural language processing, as you can imagine, into solutions that can be then deployed to production. And we'll talk about the entire life cycle of how we do that, how we systematically conduct research with the business objective in mind, and how we go through the entire process. And today I'm joined here by Zenodia, who was already briefly introduced. Would you like to say hi to everyone, Zenodia? Here we go.
Hello. It's difficult to switch between different. Hello. I'm a senior solution architect at NVIDIA. My verticals is auto and healthcare. I have a background with data science, and I have been at Azure and Telia before. So now over to you, Adam.
Sure. And as mentioned earlier, I'm Adam. I'm a glorified, effectively, a mathematician with an over-complex title, but effectively, I specialize in design and deployment of very large neural networks. And today, we'll be talking about some of the bigger neural networks that we're using today, namely neural networks that are being routinely used for conversational AI. And let me first of all start by clarifying what we mean by conversational AI. When people think about conversational AI applications, they typically think about your smart assistant. Let me just turn off the timing because I don't know why, but this slide has timing enabled. Clear all timings. Here we go. If people think about smart assistant type of applications, but at NVIDIA, we look at the problem much broader. So let me kick off this event by showing you a very short video describing what we consider a conversational AI application.
What do we think we're looking at for Wednesday in terms of layout?
这个设计的整体结构图是在没有包装或是模型前执行的。我们会需要一点时间改动。
Well, If you like, I can set you up with an optometrist to get an eye exam.
That'd be great.
Okay, no problem. We'll get you started with that. I see Dr. Lee's office is close to your home. She's really well rated in our network.
Is it snowing in Chicago right now?
In Chicago, it is currently not snowing.
I'm actually planning to visit there.
That sounds like a lot of fun. What else are you planning to do while you were there?
Find us a Mexican restaurant.
The nearest Mexican restaurant is Luna Mexican Kitchen, located at 1495 the Alameda, San Jose.
How's the weather in San Francisco?
It is currently 66 degrees and sunny in San Francisco.
My name is Misty. Nice to meet you.
What can you help me with?
I can help you with current and upcoming weather at any location, and can also provide interesting information on meteorology.
So the reason why we have been working on tools in this space is to enable the developer community to build a very broad range of applications. Applications that not only are capable of doing speech recognition, but then combining that capability with a much broader set of tasks, including a broad set of natural language processing, natural language understanding tasks, fusing the information that we gain from speech with visual information. So being able to combine user requests with the knowledge about their gestural facial expressions, and really streamline the process of building those very sometimes complex conversational pipelines. And they are indeed complex because they are typically composed out of very large number of components. So those are not just individual natural language processing neural networks. They are not just automatic speech recognition neural networks, but they are typically a combination of really a lot of models. And in the video that you saw earlier, you've seen examples of speaker diarization. You've seen examples of translation neural networks. You've seen text-to-speech neural networks. You in fact have seen face recognition neural networks, eye gaze detection neural networks in order to remove the need for keyword use, and many more. Building those applications, in fact, it requires substantially more than just state-of-the-art models. It requires infrastructure that will allow you to optimize software infrastructure, those models for production, because those models are of little use if they cannot be executed within certain latency, as well as bandwidth budgets. They require software infrastructure to be able to host a very large number of users simultaneously and cost effectively manage the utilization of computational resources, in particular the GPUs, as well as software infrastructure for hosting those models and pipelines and exposing them in a way that is optimized for individual use cases. So it's not enough to have an efficient, say, natural language understanding or automatic speech recognition model. You need to expose it in a way that is efficient for the application. So say in ASR case, in batched or streaming modes. Okay, but let's come back to the core of today's presentation. So today we'll be talking about this particular workflow, which is seemingly simple, but in fact involves quite a lot of different activities and utilities. It's a cyclic workflow because we are going through that workflow on depending on the software product that we're maintaining, typically on a monthly basis, and it involves research, optimization, and deployment. And a lot of those activities overlap. So our research efforts in a quite substantial way overlap the optimization efforts. So for example, a big part of what we have been doing within automatic speech recognition is develop models that are more and more efficient in terms of their ability to do inference. And within all of those three different tasks, we have a set of typically open source tools that that we are internally using and we are making available to the broader public to help us address some of the key challenges. So within this research space, if you wish, we're going today to talk about a tool called NeMo, so neural modules, which is an open source toolkit for building conversational AI applications. And we'll very briefly also talk about transfer learning toolkit, which is our tool for less advanced users, which is intended to hide complexity of building and transfer learning, fine-tuning models within this conversational AI space. We'll talk very briefly about TensorRT and Triton inference server. So our key tools for optimization of neural networks for deployment, as well as Triton, which is the server that we use for hosting of machine learning pipelines, not necessarily deep neural networks exclusively. And Jarvis, which is our platform that brings all of those elements together. Let's dive into a bit more detail, starting with the research. So once again, when people think about conversational AI applications, they typically think about those three broad problem areas. So automatic speech processing, that includes automatic speech recognition, but also other tasks, a wide range of natural language processing tasks, and text-to-speech. And NeMo is a toolkit that provides you with state-of-the-art models that allow you to solve problems in those spaces, but it's much more than that. NeMo is also our encapsulation of best practice. NeMo has derived from initially internal tools that our research department developed in order to build some of the models that you are using on a day-to-day basis. Models such as QuartzNet, Jasper, TalkNet, MatchboxNet, C3Net for automatic speech recognition, or algorithms such as LARC, LARS, LAMP, Novograd, which you might be using as your optimizers. They were developed using either NeMo or its predecessor, so open sequence to sequence. It's also a fairly well-established library by now, and it's quite broadly adopted by a range of organizations across the globe that are already serving a broad range of conversational AI applications. NeMo is composed out of several elements, and it's not a deep learning framework in itself. NeMo is built on top of PyTorch, and in particular PyTorch Lightning, and Facebook Hydra, which is being used in order to control the design of your neural networks and experiments. NeMo, on top of PyTorch Lightning and Facebook Hydra, provides the developers, researchers, engineers with collections that capture all of the basic building blocks that are used for development, both legacy as well as the state-of-the-art ASR, NLP, and TTS applications. On top of those collections, we provide a set of pre-trained models, typically trained to state-of-the-art or close to state-of-the-art, that one can just download from our open repository and use as a starting point for the transfer learning adaptation activity, as well as a range of user application and scripts to support end-to-end pipelines and to support some of the more difficult tasks. I don't know, for example, speech-to-text alignment for automatic speech recognition. Okay, NeMo is called NeMo, not because it's a reference to a well-known Pixar movie, but because it is composed out of neural modules, hence NeMo. You can think of neural modules as almost like Lego building blocks out of which you build your larger application. So those building blocks are things such as loss functions, decoder architectures, encoder architectures, entire data pre-processing pipelines that you can combine together in order to build individual neural networks, but also then to create end-to-end pipelines for more complex applications. Those neural modules are typed, minimizing the likelihood of making a catastrophic mistake that you might not notice. NeMo takes advantage of Hydra, which makes management of design of neural networks and experiments easier and helps with controllability of the process. It integrates with PyTorch Lightning, trying to hide as much of an implementation overhead boilerplate code as possible. And it was really designed for scalability and performance. So NVIDIA internally is devoting quite considerable amount of engineering effort in order to make sure that not only those neural modules work, but they actually work very fast. So this is by far one of the fastest ways to train some of the state-of-the-art models in this space. It also is capable of very large-scale distributed training. So whether you have 2, 4, 8, 16, or 5,000 GPUs, NeMo will allow you to train on all of them without degradation performance, and we'll go into that in a second. And then it also comes with an extensive collection of pre-trained models. So let's focus on the 3 key features, which I think are the most important, and we'll move to the next topic. So feature 1, highlight 1. NeMo provides strongly typed modules, strongly typed tensors. So all of the Lego building blocks, if you wish, neural modules, have types associated to them, and they can which are being enforced during the creation of the neural network. This allows us to ensure compatibility between modules and catch semantic, rank, or dimensionality mismatches very early on. It's actually very easy to rotate your tensors inappropriately and not notice for a prolonged period of time, what leads very frequently to sometimes days, sometimes weeks, or even more of lost development time. The way NeMo is constructed is a result of almost now 7 years of systematic research, and it's really designed to simplify the debug process so that you can get to your solutions much faster. It is NeMo, and that's feature number 2 that I would like to highlight, is taking advantage of Facebook's Hydra. It allows you to very easily manage experiments, manage variants of your neural network, and quite dramatically reduce the amount of boilerplate code that you need to generate. In most of the cases, your engineering activity, your development activity is limited to generation of YAML file describing architectures and experiments, so that you can focus on what matters, namely experimentation, rather than sometimes unnecessary software development. It is based on PyTorch Lightning, so if you want to take full control over how it's executed, you can do that as well. And in fact, we provide quite a lot of examples of how to do it. And the last highlight that I would like to focus on, it is designed for speed. Yes. It scales to multi-GPU and multi-node setups. So if you have 2, 4, 8, 16, 32 GPUs, it will scale and it will train with linear acceleration. So the more GPUs you throw at the problem, the quicker you'll get the results. It automatically supports mixed precision training, so you can take advantage of some of the hardware acceleration available in modern GPUs, in particular tensor cores. And in fact, it's on average 4.5 times faster than a naive FP32 based implementation. And it really hides the complexity of building the distributed implementation, allowing you once again to focus on experimentation. We have tested all of the models within NeMo at fairly substantial scales, in order to make sure that not only the training time scales linearly with the amount of computational resource, but also that we are not observing degradation in accuracy. In this case, since this is an automatic speech recognition example, word error rate as we increase the batch size, since this is just an implementation of data parallel training. And this is achieved by taking advantage of some of the more advanced optimization algorithms, such as Novograd, which allow us to train with extremely large batch sizes. And finally, there is really a lot of good content within NeMo. So as I've mentioned, there are 3 groups of neural modules and neural networks, focusing, first of all, speech processing, so tasks such as automatic speech recognition, speech classification, speaker recognition, and diarization. A broad range of natural language processing tasks, as well as obviously modules that are supporting development of your own custom ones, as well as both 2-stage and end-stage pipelines for text-to-speech. In terms of ASR and pre-trained models, we currently have predominantly Jasper, QuartzNet, CitriNet, and Conformer, and pre-trained models for English, Mandarin, German, and several other languages. This list is accelerating in terms of its growth, so we're adding now more languages in the next few cycles. In terms of other speech recognition tasks, we have dedicated neural network architectures for tasks such as speech command recognition, audio sentiment classification, speaker identification, speaker verification, voice activity detection, and actually quite a few others. They are designed for those tasks and typically considerably smaller than automatic speech recognition models, allowing you also deployment into embedded systems. In terms of NLP, we have a very broad collection of both neural modules as well as pre-built neural networks to solve some of the most important tasks when it comes to building conversational applications. So one of the main ones being joint intent and slot classification, named entity recognition, punctuation, and capitalization. There are also tools for text normalization and so on and so forth. The NLP models that we have right now are based upon standard transformer-based components, and we also have a Megatron-based implementation, which allows you for building very large transformer-based neural networks. In fact, we have trained just out of the box Megatron implementation with models exceeding GPT-3 largest variants, so exceeding 175 billion parameters. And finally, within the text-to-speech space, we have a number of, again, modules out of which you can build neural networks, but also 2-stage pipeline neural networks, as well as end-to-end pipelines, both components for mail spectrogram generation and audio generation, so vocoders. And this includes neural networks such as Tacotron 2, Glow TTS, Fast Speech 2, Fast Pitch, TalkNet, WaveGlow, and state-of-the-art models such as Hi-Fi GAN. And on the back of the success of those generative models, we also started introducing end-to-end pipelines. So there are early implementations of Fast Pitch, Hi-Fi GAN, end-to-end models, and so on and so forth. So it's a great open source project. We're always looking for contributors. And with that, I'll hand over to Zenodia, who will talk about module graduation. So how we actually get those models from research and mature them to land in NeMo and then in Jarvis, and then optimization and deployment.
Hi, so Adam, would you like to get to the next slide for me?
Sure.
Yeah. So you probably were wondering how does those models ends up in the model zoo in the first place. So that's exactly what I'm going to talk about in the next slide. So at NVIDIA, we consider there are 3 aspects as worth mentioning for this problem, namely ensuring code and data compliance, strive for SOTA, and high performance. We consider those in an iterative process way so that when we graduate a model into the model zoo, they are always consider these 3 elements. So let's dive into the first one. If you consider a data set, because if you want to train models, you kind of have to consider the data set first. So when you hunt high and low to check what data set is usable, it is very important for us to consider the long-term usage when the model graduates into application. So for example, that when we consider the data sets licensing, there are all kinds of licensing and then constantly changing and need to check and double check so that we have a collection of data set that is legally compliant. We have internal legal approval process in order to check if this data set we can indeed use in the end when it's come to application, when there is a possibility even of potential usage for commercial. This is important because commercial usage is very different than the academic research only usage. So if in the data set that comes with the licensing says no, then we might put it down, prioritize this data set in the later stage if we consider that we are not, we are eventually going to use it in the commercial scenario. So all of the model that you're seeing in the model zoo, they are the data set they are trained on are all going through this practice of scrutinizing, of internal approving, of checking and rechecking the licensing and making sure that the data set can go all the way through to application. The second thing is that whenever we are building any sort of model, go back, sorry. So we're building any sort of models, there's always a data preprocessing, model training and or inference, and then data post-processing process. So if we are considering the code, if we borrow code from somewhere else, then we need to do proper crediting and citing. So you would actually find it either inside of the NeMo code, citing or crediting those resources that we use, for example, like Moses to do data preprocessing, or that you will find it in the NeMo user document. We have a online and constantly updated user document. You will find, like, for example, for machine translation, you would have the data preprocessing step, the library you use, the proper pointing and the proper citing and the proper crediting to those resources as well. So next slide, please. So now let's say we have data set, a list of data set prioritized against the usage, and we are ready to train model. And then when we wanted to train the model, we need to establish a baseline against a certain benchmarking. So of course, again, we need to find an authoritative test data set for benchmarking that comes with a benchmark. An example of that will be, for example, the glue benchmark or super glue benchmark for checking the BERT embedding quality. Now, we will train the model against, this kind of prioritized list of data set, and we will add them gradually. No, please come back, sorry. No, Adam, come back to strive.
It's under control, give me a second.
Yeah, yeah, here, sorry. They have like timing something. So, okay, so we will gradually add the data set, and then we establish a baseline from the first data set, checking the benchmarking, and then we will do, for example, hyperparameter search or model architecture experiment, and adding gradually the data set to see that if we could finally converge to SOTA or approaching SOTA. Now, if the model's performance is stable and then SOTA is achieved, now we will consider for the performance because we are very close to deployment. Next slide, please. So for us, there are two things very, very important when it comes to having the model deployed to an application layer. So the first thing we consider is code quality. So as you know that NVIDIA is trying to accelerate everything onto GPU. So for example, if in your data preprocessing during the research phase, when you use libraries such as pandas, which is easy in syntax and then easy of usage, but it doesn't accelerate, right? So we will try and look for those, each and every of those data preprocessing, model training, and or data post-processing modules, if those libraries can be accelerated and those operations can be accelerated on GPU, we do it. So for pandas, for example, panda data frame, if we're using it, we will be replacing, dropping in replacement, in fact. So the syntax is quite similar. It's a drop-in replacement called QDF. So it's accelerated directly onto CUDA, the data frame. So for us, that's how we see code quality. We refactor it until that we think every acceleration is achieved and the performance is achieved. The second thing we consider is the model size. We will be talking about quantization, post-quantization for throughput later on in the next section, but the model size matters. As Adam previously said, at NVIDIA, I mean, when we deploy the model, we don't only consider the scenario for data center. I mean, data center has very beefy computing power. We all know that. But what if that you wanted to deploy the model on an edge device with limited compute power, with limited memory footprint? So an example I can give in this context is that Adam previously, when it comes to talking about NeMo, there was papers that we have published over the years. So they are also an iterative approach that we try internally in research department in order to be coherent when it comes to this kind of end goal of the data center as well as the edge device application. Now, Jasper is a automatic speech recognition models with a paper that we published in August 2019. In the next, if you have the animation up, please, Adam. So if you look at downstairs here, so here's the link to that paper. This model achieved state-of-the-art of the word error rate 2.89 on the library speech test clean dataset. This model is around 300 million parameters. This could easily be deployed in data center. However, it can be a bit clumsy, so to speak, if you want to deploy this model onto an edge device like JSON family of the device that we have. So 2 months later, there were actually countless of this experiment intensively for this purpose internally. So we published yet another paper, and this time it's called QuadsNet. This model is tiny, as you can see. It's 20 million parameters without compromising too much of the model performance. So it's not like still on the dot of the SOTA, but it's like approaching the SOTA. So we try very hard not to compromise the performance already achieved, but try to shrink and compact the model so it will fit to the edge device as well. So now we have gone through this iterative approach until that we have models that we are happy with, then they graduate into the model loop. So the next, maybe it's a really good time to talk about optimization. Next slide, please. So optimization, I'm introducing you a toolkit called TensorRT. It can take literally pretty much, the most popular deep learning framework that you train your model on, whether that is TensorFlow or MXZ, PyTorch, and so on. That was on the list over here on the left-hand side. You optimize it using TensorRT against target device. So the target device of the GPUs can be embedded in the data center, such as Tesla A100, V100, and so on. Or it can also have the capability of targeted the device at edge. So that would be the JSON family, like JSON Xavier, JSON AGX, or Drive. So next one, you might ask, next slide, please. You might ask, so why should we do optimization at all? If you look at this, if I can point here, if you look at this left-hand side of the PyTorch CPU as the baseline, thank you. If you only, this is a native code of TensorRT TTS it's a text-to-speech model. If you just simply run it as an inferencing on a PyTorch native on CPU, and we say that's a baseline, and we accelerate it by porting the code to GPU, that's the one in the middle, yes, using the T4 GPU, you already achieve 9 times of acceleration, the throughput. Now, if you further optimize it using TensorRT, as you can see, so now we achieve 13 times than the baseline of the throughput. So I hope that's clear why we do optimization at all. Next slide, please. So now, what exactly are we optimizing against? When we say we take a pre-trained neural network and we wanted to optimize against target device. So here are the 5 important things that we will go through, and this is done automatically in TensorRT. So the first thing is precision calibration. It would take your neural network pre-trained layers and check if it's floating point 32. And if you chose to want to quantize it to floating point 16 in order to, minimize the memory footprint and maximize the throughput, then it would do that automatically layer by layer. If you want to do it more aggressively and say, okay, now I wanted to quantize it to int 8, then you need to, provide a calibration data set in order to not lose the performance, because, when you do quantization, sometimes you might lose performance. So you need a held out data set for calibration. TensorRT will automatically check for the operation inside of your neural network. And if it knows this operation really well, they will fuse those operations together. And then it will accelerate it on deep learning accelerator on the GPU. So it will run faster. The kernel auto tuning is that when you have a target device that has several different parameters on a Linux kernel, then you needed to tune those parameters. So as the batch goes through the neural network, and it will tune that to the optimal performance. It also supports multi-stream execution, again, to maximize throughput. It will check the efficiency of the layers in order to dynamically allocate tensor and the memory pointers. And these are all done automatically in order to optimize against throughput on the target device. The optimized model, it's been converted to an optimized model from your neural network checkpoint, and it will be saved as a plan file ready for making inference. So now it is probably a good time to talk about deployment. Next slide, please. Yes. So as Adam previously said, for deployment, we have an open source software that is built for scalability during serving. It can serve on GPU and or CPU concurrently. It will have this capability of supporting dynamic batching, whether it is real time on the batch mode or in the live streaming mode. It supports all of it. It supports multiple deep learning framework backend. So you could have one in TensorFlow, one in PyTorch, one in Onyx, and so on. As long as you optimize them against the target device. You could even write your own custom operation plugin in order to be served. That's allowed. It has this model ensemble capability. We will see an example of this. This is what enables, among the other things, GPT-3, the largest variant of that model, to be deployed on Triton Inference Server 2 slides down. Next slide, please. So let's take a look at a little bit benchmarking. So this is from MLPERF. It's a neutral third-party organization that they are specialized in doing benchmarking. So we, as an organization, we care about those benchmarks in high-performance computing. We submit those benchmarks. It will be evaluated, and then it will be, it will be posted on their website when it's okay. So if you look at I'm not going to stay too long here, but the most important thing to look at is that the blue bars are the CPUs, and the green bars, whatever shade that is GPUs. As you can see, the dark green one for NLP or speech recognition type of models in this context are in general better than CPU. It's faster. And in comparing to ourselves, if you look at NVIDIA A10 versus NVIDIA A100, our beefiest GPU, the throughput can almost reach 4.5 times. So, well, there you have it. Next slide. Let's talk about GPT-3. Yes. So as I said previously, we have the capability using Triton Inference Server to deploy the largest variance of GPT-3, which is 18 billion. As you can see on the graph, so you can use something called Onyx Graph Surgeon. You cut, if this model is too huge to even fit on one GPU, you can cut the GPT-3 layers using Graph Surgeon, Onyx Graph Surgeon, and you cut it into two parts. And you might ask, okay, but GPU have to communicate against one another. Wouldn't that be latency? Well, we use peer-to-peer NVSwitch and NVLink to minimize that latency. So it's negligible. It's not something you need to consider anymore. Now, thanks to Triton, has this ensemble capability. So you can chain, like, this is GPU 0, GPU 1, and when the input from here will go out as the output and then input into GPU 1, no problem. So as you can see, because of this capability, we can even concurrently serve up to 4 copies of this GPT-3 18 billion. And then use this kind of way to actually maximize the throughput if you have a lot of queries and requests. Next slide, please. So what is the best combination, you might ask, because Triton can serve many different models. It can serve the Onyx runtime, it can serve the TensorRT plan file, and so on. If you look at this graph, again, comparing to CPU as the baseline, basically GPU is better, is what we're trying to tell you. And if you're looking at the yellow or orange bar, Triton plus the Onyx runtime backend serving GPT-3 18 billion parameter. The throughput, yes, is impressive, but not as impressive as the best combination of Triton Inference Server plus TensorRT as the backend. It delivers the highest throughput. Okay, so now I think that it's time to tie everything together. If you consider NeMo as a research toolkit, either you wanted to train a model from scratch, or you wanted to pull down those models that we graduated into the model zoo, and then doing transfer learning on your own data set. Once you're happy with the model, you optimize it using TensorRT. Then you serve multiple models, ensembly or concurrently with GPU and or with CPU. Then you can serve this kind of multi-model approach of the conversational AI. That's what we call Jarvis. And next, Adam will be talking about how to package it into different user cases and how we serve the enterprise-ready conversational AI.
Sure, thank you, Zenodia. So yes, so I appreciate that we have covered, really a lot of different tools, and unfortunately they are all necessary. But we have realized that this is starting to become a very complex pipeline involving a lot of different activities and a lot of disparate tools. That is why about a year ago we've decided to bring all of those tools together in a single umbrella overarching technology that we are calling Jarvis. Jarvis is our attempt to consolidate everything that you've seen so far. So to bring together NeMo, TensorRT, Triton Inference Server, and all of the common and reusable features that are necessary to build conversational AI applications. So Jarvis, as I just pointed out, takes advantage of Triton Inference Server for hosting the models. Jarvis takes advantage of TensorRT to optimize those models. Jarvis uses models exported from NeMo, or in fact from any other Onyx capable library to host those models, but it streamlines the process of doing that. And it not only, in contrast to Triton Inference Server, exposes the raw model APIs to the user, but provides an additional software layer to package into coherent APIs the most common conversational AI tasks. So tasks such as real-time automatic speech recognition, or batched automatic speech recognition, or facial landmark detection, or text-to-speech in batched or real-time mode. It is intended to hide the complexity of building those end-to-end pipelines, and it's available in open beta. And this slide provides you an overview of resources that you can use to learn more about its inner workings and request beta access. A tool that we have largely neglected, since this is a fairly advanced audience, is a tool called Transfer Learning Toolkit. Transfer Learning Toolkit is another attempt to further simplify the process of building conversational AI applications. It doesn't give you anywhere near the same level of control over the training process as NeMo does. It doesn't allow you to bring your own models and modify the neural networks that it provides, but it does implement all of the state-of-the-art models in natural language processing, automatic speech recognition, computer vision. It provides some of the more advanced features that are necessary to deploy those models to production. So for example, it supports things such as quantization-aware training. It automatically quantizes to either FP16 or Int8. It has a seamless integration with pruning. Out of the box, it will take advantage of tensor cores when both training and then deploying those models to production. And it provides a fairly seamless route for model deployment into Jarvis or other inferencing solutions. So no, it doesn't give the same amount of flexibility as NeMo, but it is designed to enable less advanced users that will predominantly care about dataset engineering and hyperparameter optimization. All of the tools that we've discussed today are available. NeMo, Transfer Learning Toolkit are open source utilities. So NeMo is an open source utility. You can get access to the code today. Triton Inference Server is again an open source utility. You can get access to it today. Both of those are very mature. Transfer Learning Toolkit is not an open source software, but it's freely available on our website. And Jarvis is at an open beta stage. It is available. You have to request access. For less advanced users in the audience, or for managers in the audience that are managing broader teams that you want to upskill, we've also identified that doing what we just described is non-trivial. So quite some time ago, more than I would say, I think 5 years ago, we've established a training program called Deep Learning Institute. Deep Learning Institute provides both online as well as instructor-led courses covering a broad range of not only deep learning, but now also high-performance computing courses. This includes courses on multi-GPU training, so on training on large GPU systems, multi-GPU systems, conversational AI, and natural language processing. For the academic audience, as part of the Deep Learning Institute program, we also provide teaching kits that we've developed with some of the brightest minds in this space, which are effectively course templates for teaching deep learning across university. Those are just freely available for people in higher education. Apart from instructor-led courses, which we provide to organize groups, we typically host on a very regular basis a number of public workshops where you can just attend as a part of a larger open group rather than having to organize a dedicated instructor-led course for your organization. I think the upcoming courses that we have in the calendar are transformer-based neural networks for natural language processing and conversational AI. The multi-GPU course is a bit off. If you're interested, have a look at the training website, check out the training calendar. And with that, I would like to open up for questions.
Thank you, Zenodia and Adam. So yeah, please, audience, pose questions. I have some of my own, but yeah.
Yeah, let's start with yours. People typically need a second or two to collect their thoughts and type them in. Or
I'm really interested to know, are you planning to somehow to put emotions in the text-to-speech module of these pipelines?
So that's already there. So emotion detection would be considered a speech classification task.
Mm-hmm.
So there are quite a few architectures for speech classification already. I don't think we have pre-trained models for classification, simply because it's at this point of time it wasn't considered a priority. We also have basic computer vision based speech recognition, sorry, not speech recognition, emotion recognition models available as part of the transfer learning toolkit. So the building blocks for that are already there. We don't have any state-of-the-art models pre-trained for you though.
I mean, for text to speech. So when
so
the car is
text to speech, sure.
Yeah.
So prosody control, yes.
Exactly.
So yes, that models such as C3net already can control some aspects of speech prosody. In fact, on one of the demos that I've linked in the previous slide, Jen Sims, our CEO, is demonstrating exactly that. Effectively, he's generating a he's entering a single text and generating multiple different speech samples depending on some settings that he's tweaking during the demo.
Cool.
Okay.
Another question would be, how do you merge layers in large models? Is there any good heuristic?
So no, those are not heuristics. Unfortunately, or maybe fortunately, we have a very large team whose sole responsibility is A, to understand the landscape of state-of-the-art models, B, profile those models and understand where bottlenecks are, and then we typically design custom written kernels that combine multiple operations together and exchange memory efficiently. So this is not something that is happening in an automatic way. There is typically a level of custom code that our team responsible for cuDNN is doing. We also have, I think, weekly calls with all of the deep learning framework teams to make sure that that complexity is hidden from the end user. So we're trying to make sure that if you create common and known linear combinations of layer, appropriate CUDA kernels are invoked automatically. This is both for deep learning frameworks as well as TensorRT. We have a very mature profiling utility, so if you want to build your own, then there are already some quite cool guides describing how to do it.
Cool. Also, OpenGPT-3 is about 170 billion parameters, right? You have the
175 billion.
Yeah. Exactly, and you have a version of with 8 billions.
No. So we have open sourced our implementation of that paper. We have not open sourced the weights, but we are quite regularly now training on models substantially above 175 billion, and working with partners such as Microsoft to get much further than that. So systematically working towards 1 trillion parameters. In fact, just a couple of weeks ago, we've published a paper describing just that.
Okay, cool. I meant only in the slides there was a 8 billion model.
18 billion, yep.
18 billion, yes.
18, okay.
Yeah, because this piece of work was designed with collaboration with some customers in Russia, and already 18 billion is a lot, and this is what they wanted to develop. That is why that was the focus of the work, but the principles are the same. It's just for more than 18 billion parameters, you would need more than 2 GPUs.
I was just wondering if you use some techniques to optimize the size and shrink that.
Yes, so bear in mind, there is nothing special in terms of the GPT-3 design. It's a very standard transformer-based neural network. So in fact, optimized kernels that we have developed for other transformer-based architectures just work out of the box. So once we slice and dice the Onyx file into chunks, we deploy to Triton Inference server, we tell it to try to attempt TensorRT optimization. So it just uses out-of-the-box optimization. So it uses out-of-the-box fused kernels for transformer to optimize them. It will attempt to do FP16 conversion and so on and so forth.
I will put the paper of Megatron LM, and it exploited the normal key value and merges in order to actually make the possibility of parallelization. And in that paper, it actually says very detailed how it is done. I will post the link too.
Yeah, but from Triton's inference server perspective, there is nothing special about GPT-3. It's yet another neural network. In fact, it's a very familiar neural network, so it treats it accordingly.
It's just, I think, also a lot of data and power behind it. So it's nice to know how to keep it small and efficient training. Yeah?
Indeed.
I also had a question about Jarvis. So do you have any actual, as a current use case where it's in use?
So
yeah.
Yes. Go on, Zenodia.
And in the I think in the first slide before when we talk about packaging, there's a lot of user cases that is already being adopted in the industrial scenarios, such as smart manufacturing, and touchless, using only voice to command. Yeah, and or when you are, for example, in the video conferencing scenario where you have a person that don't speak well English, for example, like Chinese, they wanted to have the Chinese either speaking Chinese being translated to English or having English being translated to Chinese and so on. And these are kind of regularly used user cases.
Yes.
Adam, you would like to add more?
Yeah, sure. So in fact, internally, we have already developed a product that sits on top of Jarvis. So that product is called Maxine, and Maxine is targeting all of the companies that are currently providing teleconferencing services like the one that we're using right now. So as part of that, Maxine will do things such as audio compression. So it will take audio, it will pass it through a neural network, get an embedding of that audio and transmit that instead of the raw speech, and then decompose later on. It does something similar to the face. So it can do facial compression. It will do background noise removal. It will do denoising, resolution upscaling. So it's a fairly nice comprehensive package for building video conferencing systems. It has features such as translation, and yeah, it just sits on top of Jarvis. So if you're interested, search for Maxine, NVIDIA Maxine.
Yeah, I didn't see any questions here. I would pose one more, and then maybe we have also a Q&A afterwards.
Sure.
Yeah, I still thinking about Jarvis because you are doing also multimodal on that.
Correct.
How much we had yesterday talk about multimodals. So how much does the image improve the or any other sensory the already the performance of the text module?
So it's not necessarily about improving, it's about enabling totally new use cases. So it's about things such as getting rid of the the keyword, the one that you use to initialize the conversation with the conversational AI system. So in the video that I've showed you, we're not relying on okay, whatever, but we're using gaze to establish communication, and this is important in a lot of applications. So for example, another product that we built on top of Jarvis is part of Clara, so our medical toolkit. Effectively, it's conversational AI application for clinical setting for hospitals. In that case, you don't want to rely on those keywords. You want to be a bit more proactive in terms of initiating conversation, especially when it comes to significantly impaired users. Also, go on.
I can add on to that part because I belong to the healthcare team. Basically, we have cases where, in the elderly or care home, where the elderly people sometimes just want or need something to talk to. So they can wave to speak or gaze to speech or whatever keyword that if they want to use keyword. Otherwise, they can use gesture to activate it. Yes.
Also, it injects a lot of information in ambiguous situations. So again, as part of the video, I think you've seen a situation where the system was interacting with a simulated customer in a store. And if you're in a situation like that, you might get questions such as, how much is this? Or and people will rely on gestures, gaze to kind of inject information into the conversation, and without ability to interpret that the image, you will not have that information. So you would have to ask for it in an additional step. So yeah.
Cool, thank you. If for the audience, if you want to post also in the chat the questions, you are welcome.
I'm not sure whether you have read any questions from the chat, because I was predominantly looking at looking at my screen. So here we go.
I got one.
Yeah, sure.
So Simone Grisa, she asks, based on the presented use case, the opportunities are huge. Is there an opportunity or use case you do not based on ethical or legal grounds?
Yeah, sure. So and a lot of those models will have malicious applications. So yeah, and there is we are in the process of further formalizing it. A set of that you already find on the portal that we use to distribute those models. So as part of the terms of use, you'll already find some of those listed. We are now working very hard to extend that list, but definitely. Yeah.
Would be that also a part of the vetting of the data sets, or?
So I don't participate in the process of vetting the data sets, but my understanding is that yes. Yeah.
So the data set has been monitored like on an ongoing basis. Basically, every single time any model that is ready for any application, we check and recheck and double check the data set. Otherwise, we will even go as far as train from scratch of the data set that's approved.
So, and we go far beyond the licensing of the initial data set. So for example, as part of the most recent activity to vet those, I just talked to one of our solicitors the other day. We've reached out, because we use standard data sets for text-to-speech. We've actually reached out to the people that participated in the recording, despite the fact that the license that they've agreed to was very broad. So we've reached out to them to make sure that they are happy for us to use those recordings in this context, despite the fact that they've actually agreed to it implicitly already because of the very broad outreach of the license that they've agreed to.
Yeah, and also, and also with regard, for example, like, I train a Swedish machine translation models that they are really, really good performing. However, because of one of the data sets that I reach out to the website that actually provided this data, says OMPUS. Basically, they didn't reply me, so that means that I cannot even kick off the legal approval process internally. That also means that this model might never see the light. So this is how strictly we take it. How seriously we took this kind of thing. Yeah.
Yeah. Thank you. We are already over time, and so we will meet on the key. I will share the screen briefly because the next